Okay, in this video I'm going to begin section 2.2. In the last one we kind of introduced the idea of a limit, okay, with the tangent line problem. I'm just showing you the notes there from 2.1. The tangent line problem, and then I had talked about the velocity problem. Okay, and here's two problems that I wanted you to look at on your own on page 82 there. We've looked at two examples for why we have limits, okay, the tangent line problem and the velocity problem. Now we're going to turn our attention to limits in general, and we're going to see methods for computing them. So let's take a look at an example here. Suppose that we have the function f of x equal x squared minus x plus 2. And I want us to investigate the behavior of this function for values of x near 2. Well, the first thing that I've done is I've made a graph of this function. This would be a parabola. And going back to algebra, I can know that this is a parabola that is facing up, and I can calculate the vertex. Negative b over 2a would get me the x coordinate. A is 1 and b is negative 1. Okay, so the opposite of b, that'd be 1. Divided by 2a, 2 times 1 is 2. So the x coordinate would be 1/2. If you were to plug 1/2 into the function, you should get 7/4 in return. Okay, so this point here, 1/2, 7/4, that would be the lowest point on the parabola. That'd be the vertex. And if x is 0, y is 2. Okay, if x is 1, you also get 2. Okay. Now, so I've drawn this parabola, and as I said, I want us to investigate the behavior of this curve for values of x near 2. Well, using this table again, I've set that up with values of x that are close to 2 on both sides. Okay, so here's where x is less than 2 and close to 2. And then here's where x is greater than 2, but also close to 2. All right, so like for example, if x is 1, and I plug that into the function here, 1 minus 1 is 0, plus 2 is 2. Okay, if x is 1.5, you can plug that in, and you should be getting 2.75. Okay, and I plugged in 1.9 would get me closer to 2. Right, here's 1.99, which gives me, gets me closer to 2. And then I'm selecting values that are now bigger than 2. Okay, like if x is 3, 3 squared is 9, minus 3 is 6, plus 2 is 8. If x is 2.5, you can plug that in, and I'm getting 5.75. Okay, and I'm getting closer and closer to 2. Now, to have you just see how I can get these fairly quickly using the calculator, this is an 84 model. It's going to be very similar on an 89 model, but this is a handy thing to know and use. If you were to type in the whatever function that you have here into y1, so for us, I'm going to let y1 be x squared, what is it, x squared minus x plus 2, and then hit enter. And then I'm going to hit table. I hit second graph to get me a table. Then I can select values of x, any values that I want. So like, if I were to let x be 1.99, I'm getting, okay, I'm getting 3.97, roughly, if I go nearest 2 digits. I could let x be, here's 2.001, okay. I'm getting 4.003 then, right, from this. And of course, I can let x be anything. Okay. Now, one thing that you would want here is in the table set. I hit second window to get to that. You'd want independent to be on ask, not auto. If it's on auto, your calculator is going to automatically have numbers set up for you, which we're not going to want. Okay, like I wouldn't want to be plugging in, like x equal 20 or x equal 43, or where I'm way out, very far away from 2. Okay, like I want to be very near 2. Okay, so I want to be able to ask the calculator to do calculations where I'm just simply typing in those x values. Okay, I would encourage you guys to know and use the table feature that is there on the calculator. That's a handy thing in being able to guess the value of a limit. Okay, now based on our table, it appears that f of x is getting closer and closer to 4 as x is getting closer and closer to 2. Okay, so that's the limit as x approaches 2 of the function x squared minus x plus 2, that would be 4. Okay, now that's, again, just a guess there. Now, one thing that you probably could very easily see here in this problem is that, okay, well, if I just plug 2 into the function, 2 squared is 4, minus 2 is 2, plus 2 is 4. Okay, so I could have known that, f of 2 is 4, right? So, like, why do all this? Well, that's not what the problem is asking. I don't care what's happening at 2. Okay, I care what's happening around 2. I want to know what's happening near 2. And that's the whole idea of a limit. Okay, in calculating a limit, we want to investigate the behavior of the y values for x values around some number, not at the number though. Okay, and here's just kind of an informal definition. We write the limit as x approaches a of f of x equal L is how we would read that equation, and that's how we say what I have written there. If we can make the values of f of x arbitrarily close to L, in fact, as close as we like, by taking x to be sufficiently close to a. On either side of a, you can be on either side of the number, whatever the a is. So in this problem, a is 2, okay, but not equal to a. The conclusion of that is very important. Okay, like in this problem, I don't care what's happening at 2. I don't care that f of 2 is equal to 4. An algebra student can see that. Okay, what's happening around 2? Well, that's a different question, right? So that's what we're interested in here in describing a limit. Okay, we're not allowed to choose the a value, but we'd like to know what's happening around that number. Let's take a look at another example. Okay, in this next one, I want us to guess the value of the limit as x approaches 1 of x minus 1 over x squared minus 1 numerically. Well, f is not defined at 1. We can see that because there's a problem with division by 0. Okay, x can't be 1. 1 is not in the domain of the function, right? But we don't care about that, right? We don't care what's happening at 1. We care what's happening around 1. So let's use the definition. Okay, let's take values of x close to 1 in this problem, but not equal to 1. So I've got my table set up here, and I've selected values that are less than 1 and then values that are bigger than 1. Okay, and I could, of course, I could use my calculator. I could go back to the y equals screen there and type in this function. Here's x minus 1 divided by x squared minus 1. Okay, and hit enter, and so then I can go to the table now, and of course I can clear out what's already there. So, like, suppose that x is 0.5. Okay, if x is 0.5, we get 0.6 repeated. Okay, what if x is 0.9? We get roughly 5.26. Okay, what if x is 0.99? Okay, I get roughly 0.503 if I go nearest 3 digits. Okay, I'm not picky about the rounding here at the moment. In the book, they'll tell you where to round, okay? So I would continue selecting values that are close to 1 on either side, and I could see what's coming out of the calculation then. Now from our table here, it would be reasonable to guess that the limit as x approaches 1 of this function, x minus 1 over x squared minus 1, is 0.5. It looks like the y values are getting closer and closer to 1/2. Okay. Now, suppose that I change this last example up slightly. Okay, let's look at another one here. In this next example, let's let g of x be equal to a piecewise function. For piece 1, I'm going to use x minus 1 over x squared minus 1. Now that's what I had here. And we're going to use piece 1 if x is not 1. Okay, again, I can't divide by 0, right? And then for piece 2, I'll use 2 if x is 1. Okay, so I've got this function defined for all x, and I want us to find the limit as x approaches 1 of g of x. Well, I've sketched a graph here, and a graph is helpful if you're a visual learner. Now, with this problem, x squared minus 1 is in the denominator, right? So x can't be 1 or negative 1. Now, I don't have it showing here, but if I were to include the scale further on the left, there would actually be a vertical asymptote at x equal negative 1. Okay, so the curve would be heading upward, but it's approaching a vertical asymptote, x equal negative 1. Now, x squared minus 1 factors as x plus 1 times x minus 1. I've got an x minus 1 in the numerator, which can cancel with the x minus 1 that would be in the denominator. The fact that those x minus 1's canceled means that I will not have a vertical asymptote at x equal 1. But instead, I'll have a hole in the graph at x equal 1. In general, with a rational function, if it simplifies and you have factors canceling, the corresponding zeros would create holes in the graph. Okay, so like I said, in this problem, x minus 1 is going to cancel with x minus 1. Down under, 1 would be the 0, and what I mean by 0 is 1 is the number that creates 0 in the denominator, like 1 is a problem. Okay, so at x equal 1, I'm going to have a hole on the graph. In simplified form, okay, you would have 1 over x plus 1, after you cancel those x minus 1 there. So I've plotted additional points. And of course, the fact that I've already got something very similar to this previous example, I've already been able to plot points from this table that I've made earlier. Okay, so like if x is 0.5, well, you're going to use piece 1, right? You're going to use piece 1 anytime that x is not 1. So if x is 0.5, I'm going to plug that into piece 1, and I get 0.6 repeated. Okay, so that point would be about right here. If x is 0, negative 1 over negative 1 is 1, right? So here's 0, 1 on the graph. If x is, here's 1.5. Okay, the y value is 0.4. Well, that'd be about right there, right? If x is 2, 2 minus 1 is 1, and I'm dividing by 3. 1/3 would be the output. 1/3, of course, is less than 0.4, so this point would be lower than the one over here. And I would begin drawing this curve. Now again, there's going to be a hole in the graph at 1/1/2. Now I mentioned that x minus 1 over x squared minus 1, that simplifies to be 1 over x plus 1, right? Because the x minus 1 is canceled. So I'm looking at 1 over x plus 1. Well, if x was 1, and you plug that into 1 over x plus 1, you'd get 1/2. Okay, so that at that spot there, I want that point not to be on the graph. Now, if x is 1, you're going to use piece 2, which means that you'll get 2 as the output. Okay, so piece 2 is essentially saying that the point 1, 2 is on the graph. So we're still going to be defined at 1, in this function here. Okay, now we want to find the limit as x approaches 1 of g of x. Well, what some students might feel like saying here is that, well, the point 1, 2 is on the graph, right? Yeah, but we don't care about that. We care what's happening around 1, not at 1. G is going to have the same limit. Okay. G is going to have the same limit as what we did here, which is 1/2. Because the process would be the same, right? If I'm only interested in what's happening around 1, well, if I'm setting up numbers that are very close to 1 on either side, I'm going to be using piece 1 all the time, and I would get the same output that we saw here. Okay, and it looks like we're approaching 1/2. Okay. Now, the point of this is to say, don't get a limit calculation confused with just simply plugging a number into a function. Okay. I'm not asking you what is g of 1. G of 1 is different from the limit as x approaches 1 of g of x, right? G of 1 is 2. The limit as x approaches 1 of g of x would be 1/2. Two different things. Okay. So don't get those mixed up. Okay. We're still taking values of x close to but not equal to 1. And we're still getting the same results. Okay, so this table here that was in the previous example would still apply. Okay, we'll stop right there.